Hello guys, welcome back to my lecture. Today we can talk about nuclear force, binding energy, and mass defect. So before I dive into today's topic, let's look at these terms first. Nuclear force. As you can see here, nuclear force deals with nucleus, right? So that's important to note. And the binding energy, say let's say there's a one substance here or any kind of particle right here, and there's another particle right another here, right, and they are bind with each other. Let's say maybe they have some kind of binding energy. Think about that way. Mass defect, let's say, oh, you have initial amount was like, oh, like this much, right? Now let's say this same kind of the mass or whatever the particle is, let's say over time what you see is, okay, the amount is like this much. So what does that mean? So that means the amount was decreased. Why is that? Where does the other amount went, right? Type of thing. Why do I see that kind of defect in the mass? So that idea is called mass defect. Okay, so before I explain these three terms, I need to give you some background information right here. As you can see here, there are four fundamental forces that you need to be aware of. One of the force is called gravitational force. Another is called electromagnetic force, which is electrostatic, and the magnetic force, right? Two forces combined together. And there's a weak nuclear force, and there's a strong nuclear force. What we know about gravitational force is if there is a mass m1 here and another mass m2 here, let's say this is m1 and m2, and you separate them at a distance of d, then you can have this gravitational force. So we're dealing with mass here. And the relation is also there is a mass and the distance are very important while we're talking about the gravitational force. If you look at the electromagnetic force, especially electrostatic force right here, what you see is there is a charge Q1 and there is a charge Q2, and they are separated by a distance of r. Okay, this is Q1 and this is Q2. They're going to feel attractive or repulsive force, and it depends upon the charge they have. So that is electrostatic force. In the case of F of B, which is a magnetic force, you see that the relationship is there's a charge, there's a velocity, and there's a magnetic field. Let's say electron goes through this magnetic field, right? What's going to happen is electron has a negative charge. It will bend in the magnetic field and usually make that circular type of path, and that is due to that magnetic force. This electron going to face. What about the positive charge? Okay, it will also bend, but the bending can be in the opposite direction, right? It can be in opposite direction because the charge is different. But what about the neutron though? Neutrons are chargeless. Let's say they don't have any charge, right? If the neutron does not have charge, nothing will happen, right? And the neutron does not have charge, the value of Q will be what? 0, right? So then magnetic force will be 0. Think about that way, okay? Now, I'm not going to go that much in detail there, but the idea is here, right? You need to think about when you're talking about gravitational force, we're talking about mass. When you're talking about electromagnetic force, we're talking about charge, okay? And that's very important. And the distance play a vital role here. But the terms that we initially described, nuclear force, binding energy, and the mass defect, we're all talking about this nuclear force. And we said nuclear force deals with this nucleus right here. So in the nucleus, you have a positive charge, which are protons, and you have a neutrons, which are chargeless. And you can see electrons, moving around those positively charged. And we know that there is a electrostatic attraction between positive and the negative charge between electron and the proton. But think about this way. So look at here, inside this nucleus there is a positive charge, and why they don't repel then? We know that electrostatic force said that positive charge repels. They should repel, right? Electrostatic says that, and they should attract each other, right? and that's also electrostatic said that. But in the case of nucleus though, that's not always true. That's why we're talking about nuclear force here, and they are weak and there is strong. We need to understand that. So look at here. So what is the binding energy? Binding energy is basically means when you bring these nucleons, again the nucleons are protons and the neutrons, not the electron, okay? Whichever present inside the nucleus, those are nucleons. If you bring those nucleons together here in this case, right, or you can move them apart, right, what's going to happen is you need some kind of energy to separate them, or when you bring them close together, you're going to liberate some energy, and that energy is called binding energy. What about the mass defector? Okay, think about this way. This term was not quite understandable before Einstein, right? Because he gave this equation. This equation is going to explain what mass defect is. Okay, think about this way. So what's going to happen is, let's say you have a mass, or let's say you have a mass of m1 or whatever. I don't know how you're going to explain it. What's going to happen is, if it goes through, let's say, decay process, right, and it's going to go to decay process, okay, you have a daughter nuclei now here, right? Now the daughter nuclei is small than the parent nuclei, and the mass is different. Okay, you feel like there is an apparent change in the mass. Okay, and now if the mass is changed, then where does that mass goes? And that mass will go to the energy. So that is well explained by the Albert Einstein here. E equals mc square. Okay, so the main idea here is you feel like there is apparent mass loss, but it is not actually the loss. Think about conservation of energy. Okay, what's going on here is mass is changing, or I don't want to say change, is converted to energy, let's say, right? Conversion is going on there, or transformation, whatever you want to say, but the mass will look like, you're going to feel like there is apparent loss, but in reality the mass is changing the form in the case of energy in this particular case, right? And again, this equation is very powerful. Energy E, m is mass, and the c is the speed of light, and this is pretty important for the MCAT. Okay, so here is the I'm going to go through some summary or whatever, the wrap-up thing. So if you're talking about a strong nuclear force, we're talking about holding nuclear very tightly. Okay, think about that way. When you're talking about a weak, let's say it actually responsible for radioactive decay. Something happens, unstable nuclei go through this process, which will liberate energy, or liberate energy, and it also liberate a particle, and it is not all the case the particle. Sometimes it just releases radiation in the case of gamma ray decay, right? Gamma decay, let's say. So there is a radioactive atom, there is a charges in the nucleus here, right? Positive and the neutron, the chargeless type of thing. When it's going to go that through the decay process, you will actually get some energy in the case of radiation, or you can get energy in the case of particle, right? And this is very important. In the case of electrostatic though, you have a positive charge, right, which is a proton, and there is an electron. They have electrostatic force, and we know that positive and the negative charge attract, but inside the nucleus though, there is a positive charge. They are binding because of that strong nuclear force. How that happens, it all depends upon the distance. If you are at a certain distance, this positive charge will behave as an attractive type of force rather than the repulsive type of force, and that is very important thing to note here. Okay, and that range is very short range, and it's not going to happen all over. You cannot just keep increasing the distance between those charges, but the main idea here is at certain distance there's a nuclear force which overrides or dominates that Coulomb force, which is the classic type of electrostatic force. In the case of gravitational force, we're only talking about attractive type of thing, right? When you're talking about other thing, we're just talking about attractive one. And again, electrostatic and the gravitational force have infinite range, okay? But in the case of nuclear force, though, we're talking about the range, right? Some strong nuclear force, they have it that and those weak nuclear force, right? And they have to have that meet that criteria of distance, how far you want to place them, and how that's going to affect they're going to be attractive or the repulsive in nature. Okay, again, electrostatic force is attractive and repulsive, but gravitational force is always attractive. Okay, finally, what I want to show is, okay, this is not essential, but this is what's going on here. If you're looking at this figure, this is all about nuclear force. What you see is there is a repulsive in the y-axis and there's attractive on the y-axis also. And this is a force between those nucleons, those protons and the neutron. And what you see is you see a strong nuclear force at a short range, and you can see it's going down, right? And at maybe, let's say 1.2 maybe, or almost right here, right? And there is think about this way, okay? It's multiplied by 10 to the power negative 15 meter, okay? Which is very, very small distance, right? And that if you go all the way down here, this is a peak, right? So here you have a very, very attractive force. You see the nucleon will attract very nicely in this particular case. But look at here. In the case of Coulomb repulsion force, though, these are long range, right? These are long range, and you see a Coulomb repulsion like pretty much if you're thinking about probability kind of thing, right? You see more Coulomb force than the nuclear force, and nuclear force only works at a certain range of that distance, and that's the very important thing. So distance is the key thing here. Distance between those atomic particles, let's say those protons and the neutrons, is critical. Okay, so that's it. All right, thank you so much for watching.